Welcome to the Explainer. Today we're diving into how mathematical models work, why they sometimes spectacularly fail, and how we can actually build our very own toolkit to graph these complex polynomial functions entirely from scratch. Whether you're tracking a disease outbreak or predicting economic trends, these tools are literally the foundation of understanding our world through numbers. So let's just jump right in.
Let's start with reality. You remember 2020, right? Our lives were completely upended, and scientists were desperately trying to make sense of the future. They used models just like this one, plotting data points over time to track the spread of the COVID-19 virus. They created polynomial functions to draw a clean line through all this real-world chaos to help predict what was coming next.
But here is the crucial catch. These models are incredibly powerful for a specific, narrow window of time, but if we extend them too far into the future, they completely fall apart, they break down. And to figure out exactly why they fail, we need to understand the underlying behavior of the mathematical engines powering them, the polynomials themselves.
So to solve this mystery, we're going to build a modeler's toolkit step by step. We'll cover real-world polynomial models, predicting end behavior, finding the zeros, multiplicities, and turning points, the intermediate value theorem, and then we'll wrap it all up with a complete graphing strategy.
All right, part one, real-world polynomial models. Let's look at the actual anatomy of these equations.
The defining visual characteristic of a polynomial is elegance. For a graph to be a polynomial function, it has to be completely smooth and continuous. That means only nice rounded curves, no exceptions. When the rules are broken, you get sharp, jagged corners or sudden breaks in the line. Basically, if you see a jagged edge, or if the equation has a fractional exponent on a variable, you are absolutely not looking at a polynomial.
Moving right along to part two, predicting end behavior. Let's talk about those extreme left and right edges. And this brilliantly illustrates exactly why end behavior matters out in the real world. Take a look at this model tracking HIV cases over time from 1983 onwards. It looks perfectly fine in the middle, right? But if we follow the polynomial's right-hand tail, the graph eventually plummets straight downwards, mathematically predicting a negative number of cases. Obviously, negative cases are a physical impossibility. This proves that if a function decreases without bound over time, model breakdown is completely inevitable.
So how do we predict where those tails go without just wildly guessing? Well, we use the leading coefficient test. It all comes down to determine our equation with the highest power. The degree, whether that highest power is even or odd, tells us if the ends go in the same direction or opposite directions. Then we look at the number in front, the leading coefficient. Its sign, positive or negative, acts kind of like a steering wheel, telling us if those ends point up to the sky or crash down to the floor.
Okay, part three, finding the zeros. We've got our starting and ending gates, but where does the actual action happen in the middle?
To draw the middle, we need checkpoints. Mathematicians call these checkpoints zeros or roots. Simply put, these are the specific, exact values of x that make our entire equation equal to 0. Visually, these are pure gold for us because they're the precise spots where a polynomial touches or crosses the horizontal x-axis.
To find these spots, we just take our polynomial equation, set it to 0, and factor it out. By breaking the equation down into its individual pieces and solving for x, we magically uncover the exact coordinates of our x-intercept. Notice those specific points at -3, -1, and 1. Those are our anchors. We pin those firmly to the grid, and we know for a fact our curve absolutely has to hit them.
Which brings us to part four, multiplicities and turning points. Once our drawing pencil hits one of those x-intercepts, what do we actually do?
Do we punch straight through the border to the other side, or do we bounce right back the way we came? This exact problem is solved using a concept called multiplicity. When you factor your equation, look at the exponent attached to each factor. If that exponent is an odd number, like a 1 or a 3, the graph aggressively breaks right through the axis. But if the exponent is an even number, say it's squared, the graph simply comes down, touches the 0 point, and smoothly turns right around. It's exactly like bouncing off a floor.
Part 5. The intermediate value theorem, for when the math gets a little messy.
Bouncing and crossing is great when the math is clean, but in the real world, finding those zeros isn't always as simple as easy factoring. That's where the brilliantly simple intermediate value theorem comes in. It tells us that if we plug in a point A and get a negative number, meaning we're below the x-axis, and we plug in a point B and get a positive number, meaning we are above it,
Well, because polynomials are perfectly smooth and continuous, the line is mathematically guaranteed to cross the zero line somewhere in between. We might not know the exact decimal point yet, but we know for a fact a zero is hiding in there.
Finally, part 6, graphing the complete strategy. Let's take everything we've learned and draw from scratch.
Here's your full 5-step toolkit. Step 1, check the ends with the leading coefficient test. Step 2, plot your x-intercepts by factoring. And remember your multiplicities so you know whether to cross or bounce. Step 3, find your y-intercept by plugging in 0 for x. Step 4, use any symmetry to save yourself some drawing time. And Step 5, check your turning points. A polynomial of degree n can have at most n-1 turns. This is your built-in safety check to make sure you didn't accidentally draw too many squiggles.
And bam, here is the payoff. Combining our end gates pointing down, our crossing point at -2, our bouncing touch point at 1, and connecting them all smoothly through our y-intercept, a perfectly elegant continuous curve reveals itself exactly as the math predicted. No guessing required whatsoever.
We've built an incredible toolkit today, but I want to leave you with this provocative thought. Now that you know, mathematically, that every single polynomial is destined to rise or fall infinitely at its ends, how much trust should we put in these models to solve our very finite, incredibly nuanced real-world problems? They're brilliant for a snapshot in time, but the math tells us that eventually the model will always break. Thanks for diving into this with me on The Explainer, and I'll catch you next time.